We are live now. Wherever you can start.
Okay, sir. Thank you so much. A very, very good evening, everybody. This is Bhairavi, your moderator for today's industry expert session. Hope all of you are doing great. In today's session, we are going to understand quantum computing and its relevance in today's world. To help us out with this, we have Mr. Nikhil Malhotra with us. Sir is the Chief Innovation Officer and creator of Makers Lab, a unique incubator space within Tech Mahindra with 22 plus years of experience. Sir is also a World Economic Forum AI Fellow working on responsible AI and quantum ethics. Sir has been a researcher all his life and is now leading the growth of AI, robotics, and quantum computing research within Tech Mahindra. His area of personal research has been how quantum computing and neuroscience would inspire the growth of AI. He consults various businesses and academic organizations on the future of AI and quantum. He has won numerous awards, including the 2020 and 2021 Innovation Congress Award for the most innovative leader in India. Sir is also a TEDx speaker and an author of a bestseller book, Courage, The Journey of an Innovator. We are really excited and grateful to have you here with us. Thanks a lot, sir, from the whole IITM BS degree team. So without any further ado, I would like to request sir to begin today's session. Over to you, sir. Thank you.
Okay, thank you so much, Bharvi, and thank you for the extended introduction. Although part of it is not what I should be doing, but and thank you so much for the adulation. But guys, I know there are different people from different branches who've actually joined. Some of you may know quantum already. Some of you may be doing it as a as the first thing that you've looked at it, maybe for the first time. So what I'm going to do today is actually take you through two or three facets of it. Number one, what exactly is this field? It's a slightly non-trivial field in which we are getting in. Obviously, there's a change up on the horizon because the fabric of computing will change in the decade upon us. There's a lot of practical examples that are now coming in for quantum. Obviously, today what we do is very noisy quantum, but we would be looking at in another 3, 4, 5 years, or maybe in the decade, that quantum actually touches each one of your lives. And when you actually leave college, or when you join an industry, this would have become a kind of buzzword by that time. So what I would do is I would ask you to remove your common sense hat after a certain period of time, because it does get non-intuitive or counterintuitive. And for that, I've actually started off with a very interesting quote from Richard Feynman himself, saying that I can safely say that no one understands quantum mechanics. What he really meant was there are very few people who understand the nitty-gritty of what quantum mechanics is. And quantum computing is just the derivative of that quantum mechanics itself. So let's start off. And I think I'll start off with terms and glossary. And I think what I would talk about is the moment I use the word called classical and classical world, I'm actually talking about the world that you and I live in, or you and I experience when we experience Newtonian laws as well. When I talk about quantum world, I would just jump into a universe which is about smaller particles, which is about particles on electrons, protons, and neutrons, and maybe even smaller like quarks. When I talk about bits, I would of course be talking about something that you are doing at your today. A bit is zero. It basically varies between 0 and 5 volts as terms of voltages that you give to the transistor. But the moment I talk about qubit, I'm actually saying that there's a superposition of this subatomic world where 0 and 1 both can collide and both can exist at the same time, or as a superposition combination of the two. When I would talk to you about classical computing, I'm just talking about what you do in your daily lives. And when I talk about quantum computing, I would talk about things that we are now provisioning using these small particles, and we're using universe at its basic, at its primal sense. Now, this is a great photograph from 1927. It is essentially the entire brain which went behind setting up this field for us today, which was quantum mechanics. This was the Solvay conference in 1927. Of course, you can see a lot of people that you know Einstein, you know Madame Curie. You also have Wolfgang Pauli, you've got Heisenberg, and so many others. And these are people that you've studied either in 12th standard physics, 9th standard physics, or you've also gotten to some of their formulas when you actually did your engineering or engineering mathematics and mechanics as well. Now, these people were really the fundamental architects of what we do today. But I think before these people went into this conference and what they did, I think humankind has always been very, very, if I may say, we want to find out what's the perspective of what we've made of, right? What is human life about? What's at the fundamental level that we are really made of? And that is really the point at which physics and science really starts. And I think I don't want to tell you much more over here. There's always been a quest for indivisibility. All of you have read this in your ninth standard. You've read it in your 12th standard as well. First model of an atom. This was, of course, Thomson's plum pudding model. Thomson had nothing better, but he said that, look, the atom is like a watermelon, where, if you can look at the red parts, they're all protons or they're positively charged particles. Protons was not a name that was given at that time. Whereas electrons are interspersed amongst this. These are like beads, or these are like beads that you find in a watermelon. Very, very simple model. We, of course, know that Thomson's plum pudding model was wrong. Of course, atom has a very different structure that you know today. I think the best example in pop science where you can get an example of somebody getting to the structure of atom was Rutherford. And all of you know this. You've actually seen this, Rutherford performing the gold foil experiment. Rutherford took alpha particles, which are positively charged particles and are very heavy. He bombarded a gold foil. You obviously had a blue ring, like, a kind of detector. And he detected, basically three things. He said, look, most alpha particles actually pass through this foil undeflected, which really means that atom is really empty space if this gold foil is made of atoms. So they really don't touch anything and they really pass through that. Some of these alpha particles get deflected by small angles at about, it may be 120, 30, whatever, which really means that there is the center part of the atom is positively charged. And because it's positively charged, and we know the story of how positively charged and positively charged particles attract each other or deflect each other, these would be deflected because the center is positive. And very few, about 0.01% of these particles really ricochet back at an angle of about 160 to 180 degrees. And that is the reason why I think that the center of the atom is very, very positively charged, whereas the large part of the atom itself is very, very empty space. So people just got the first view of what the atomic structure was during this experiment from Rutherford. Of course, this experiment is called hard scattering. There are certain other things that we do now, as scientists in large hadron colliders are essentially making two or more protons at very, very high speed that are actually, talking, or they are colliding with each other. Where we've also figured out that the proton itself is not a fundamental particle. It's made out of two more fundamental particles, which has got two up quarks and one down quark as well. So it's got a fractional charge in the quark as well. We won't go into particle physics, but what we are essentially explaining is that the structure of atom, the quest for indivisibility for humankind, really went us through really in the subatomic realm and say, look, we are all made up of these particles as well. And then there is light. I think during my studies of physics and my engineering courses, while you were doing it, I think one thing came up very, very prudently. And whenever we discussed light, we thought that light is both weird and awesome. Obviously, because of Young's double slit experiment, which I'm going to talk about, but light kind of behaves in very separate ways in separate environments. One thing that was done, which is the fundamental experiment in pop science or science that was done by somebody to say that you live in a dual world, the universe is dual, was actually done by Thomas Young. What Thomas Young did was he actually took a bullet sprayer, and if you look at bullets, you can consider them as particles. And he took two slits. He's covered one slit, and he found out the result at the end of the day. And he thought that, look, when you have a bullet sprayer which is actually spraying bullets across a slit and you cover one slit, most of these bullets, which is a sandpit at the end as a detector, would actually huddle themselves in a probability distribution as shown below. This is Bell's probability distribution, very typical Gaussian curve. And it's also natural because anything closer to the slit will have more bullets over here. On the other hand, if you cover slit 1 and you open slit 2, you find something which is very similar on the slit 2 side as well. And if you open both of them, you would find that this is a kind of addition of a graph, and there's a combination which comes as an addition. Great. So bullets behave as particles. We know how they behave. They can't cross through these slits. But when they come on the other side of the slits, they actually adjust themselves or engage themselves in some kind of a probability distribution that is shown over here. A similar experiment was done with light. And this is an experiment that you can do right back at your home. If you take a cardboard box and you open up 2 slits to it and shine your torchlight through it, you would see that light would appear as a wave at the end of the day. Now, that's very common. The first instance for light to behave was a wave, because you can see patterns of dark and light which comes on your screen, which could be your wall as well. And that really meant, because this is an interference pattern, this interference pattern can be shown only by a wave. And we've seen this when we drop a stone in ponds or in water. You would see waves crossing across, you would see waves huddling together and waves creating that kind of an interference pattern. All great and all good. The problem was that when we looked at a subatomic particle like an electron, which we think of it as a particle and which we compare it like a bullet, and we open just one slit and we keep the other slit off, the electron behaves like a particle exactly. It really states that it has got the same probability distribution as you would get from a bullet. And on the other hand, close slit 1 and open slit 2, it behaves exactly the same time on the other side as well. But the real change really happens when both slits are open. If you open both slits, this electron wave or electron system that comes through these 2 slits starts behaving like a wave. There are patterns of dark and light that start appearing on that screen. Now, this is so confusing, and it was confusing at that time, that how could a particle, which was supposedly a bullet particle or like a bullet particle, start behaving differently when both slits are open, and when one slit is closed, it starts behaving in a very different fashion. Of course, there were hundreds and thousands of experiments done, which really left to that point saying that fundamentally in universe, everything that you see is essentially a wave-like pattern. When you catch that wave, and you would have read about Heisenberg's uncertainty principle, when you catch a wave which you are not probable of finding out, that particular system starts behaving like a particle. And when you leave that wave away or that particle away, it starts becoming a wave again. So the universe that you live in is very dual in nature. And when you say dual in nature, all of us are made of these particles as well. We're made of electrons, we're made of protons, etc. But when these particles and their waves collide and you catch them or you try and measure them, they start behaving like particles. But if you leave them, they start behaving as waves in the sense. And of course, this particular theory was also propounded by Einstein. All of you know Einstein's photoelectric effect. Photons traveling on a piece of plate of metal emit electrons, but they are not really dependent upon the intensity. They're dependent upon the energy, which is really a function of h nu, which is the value of frequency that these protons, electrons comes, right? So the idea is that the light wave in itself consists of smaller particles called the photons. And these photons, when they strike this metal plate, they have the energy to pick up the electrons and eject them in a certain way. This got Einstein the Nobel Prize. Frankly speaking, Einstein never got a Nobel Prize for his theory of relativity, but it was photoelectric effect which got him the Nobel Prize as well. Now, a fun fact about this. Sorry, was there something?
டிவிக்கு சொல்லியிருக்கேன், அவர் தான் ஃபிக்ஸ் பண்ணுவார் நாளைக்கு. கிளாம்ப் வாங்கணும்ல.
Okay, there's someone speaking.
டெலிவரி பண்ணுறேன்னு சொல்லியிருக்கான். ஈவினிங்குள்ளே டெலிவரி பண்ணுறேன்னு சொல்லியிருக்கான். கண்டிப்பா.
All right, guys, can you mute somebody who's actually there? Sorry, I'll go ahead otherwise.
பண்றேன் ஐயா, பண்றேன்.
Actually, the Aishwarya ma'am, can you please check out, because I cannot see who's unmuted themselves.
Okay. It's probably somebody was there. So, all right. So I'll give you a very interesting fact, which I got more from my friend who's actually working at the CERN system. So what he said was that, look, this is actually true. If you really look at the point where these two particles really meet together, which we try and find out in an LHC kind of a system, you would find that the point at which these particles meet, it actually appears like a wave. It actually appears liquid. And this is normally called the Rig fireball. It's also called the gluon plasma, which really accrues to the theory that at the fundamental level, all of these particles are really waves. And when you catch them, they become particles at the end of the day. This is exactly, it's a very, very funny liquid. The time is that the time it takes for light to actually cross a coffee cup that you're drinking, it's exactly the same time that it does. So for one fact that we know is that the universe that we live in is both dual in nature. It's got a wave nature and it's got a particle nature. At the fundamental level, all of these are waves. When you catch them, they become particles. And when you do catch them and leave them away, they become waves as well. The reason why we can see each other and we are not probabilistic is because some of our wave functions are colliding with some of the wave functions around this room, right? So I am being hit by a table, my wave functions colliding with this particular PC, so on and so forth. Okay, so why should we be excited, right? This is all science, this is all physics. Let this be with physicists. Number one is that the entire process of this facet of quantum, which was quantum physics, is now gaining momentum in terms of computing. And it's no longer science fiction as it was supposed to be about, maybe 5 to 7 years back. Its practical use cases have started emerging, which I would show you some of the practical use cases, and we will also get down to mathematics and some of those scientific facets of how quantum can be worked out. Number two, there are some complex scope problems in society which have not yet been solved by classical computer. A simple problem is optimization. I know there are a lot of people who might be doing AI in these BSc courses in IIT, but if you look at it, AI has already only touched the surface of what it can solve. And I can give you one example of what AI would not be able to solve, and not even supercomputers would be able to solve. If you consider yourself in your class, and if you look at yourself, let's say there's a class of 20 people, and you want to arrange all of those 20 guys in terms of their gender, their race, their preferences and politics, and so forth. If the number of features increase, it's almost a factorial increase in terms of what you can do. So if there are 20 things that you want to arrange your people in, you are almost looking at 20 factorial value, which is a huge, huge number which supercomputers and some of the best computers can't solve. So you are looking at some problems in society which are today not solvable by classical computers. Second problem is really the problem that emerged because of the epidemic and pandemic, which we have all gone through. And we have seen that how some of the industries and some of the pharma industries are looking at drug manufacturing or making new drugs or even vaccine. We were very lucky that the vaccine that came out in 1 year could solve the challenge, and we are now open and free. But I think these are hundreds and thousands of other viruses and vectors which would need a kind of therapeutic drug and a molecule to that. Now, in order to find a molecule, you have to understand the protein part of it, and you have to fold the protein in a certain fashion. That today, even with the biggest of computers, we cannot understand a molecular formula better than chai or caffeine. If you've seen caffeine, it's a very, very small molecule. And we can't even formulate the caffeine molecule in terms of different propositions that vector would go to or that molecule would get in. So that opens up computational requirements for us. Thirdly, we think that the end of computing, classical computing, has reached. And when I do that, I'm only saying is that today we see that every little object or every little thing that you have with you is essentially made out of transistors. And these transistors are very large scale integrated into one particular component. So this mobile phone that you have in your hand has almost the equivalent amount of compute power as there was in Apollo 13. Now, imagine this has been possible because a large number of transistors are now integrated in very large scale integration design. Now, at this point in time, we are looking at levels of, let's say, 14 nanometers to 4 nanometers to which these transistors can grow. If these transistors come down a little bit, let's say about 2 nanometers, about 3 nanometers, then you would start having quantum effects, and your normal computer would not solve the problem and will have errors in the calculation that it does. So there is an edge that is reaching. This is my prediction that 2025, you might see a complete demise in terms of VLSI chips, right? So in terms of packing transistors. And this is basically Moore's law, which Moore said that every 15 months, the number of transistors that can be packed in a particular device and the computing power would double up. That may not double up, and that is why we may have to shift towards this other format of computing. And the last format in which you should be excited is that up till now, there's been a global dependency on energy which has been completely unsustainable. And I'll tell you the reason. all you use today in terms of computing power, whether you're using your own normal computer or using a laptop or using a GPU, you are using a von Neumann's architecture, which is of course inspired by the facet that you take a calculation, take a problem, break it down into smaller parts, put some of the parts into memory, start computing on some parts, and then create an output out of that problem so that you can solve a particular challenge through computers. Now, this particular process of going from input to output is completely irreversible at this point. You cannot bring back the input from the output after it has passed through. And as a result of that, you're utilizing a large amount of energy, which has gone into an irreversible operation. Quantum computing, by definition, is actually a reversible form of computing that we should utilize. So let's start with some common sense. And we know I've already talked about superposition in some way, but some common sense that you may apply is in a typical classical world that you look at, you would see that the light bulb can either be switched on or off. A bit can either be 0 or 1. And in the quantum world, it completely becomes counterintuitive because this bit of 0 and 1 can actually take a superposition format or something in the middle of 0 and 1, which allows us to compute much more faster. An example that the industry will shift across is basically the security part of it. And all of you transfer your files across to your teachers, amongst yourselves, you talk on WhatsApp, and there's a lot of encrypted messages that are sent across. One of the best theorems or formulae for encrypted mechanism is RSA. And the mechanism for RSA is typically based out of a factorization method. If I give you a number called 48 and I say 48 equal to A into B, find out A and B for me, you would immediately jump and say, look, A and B can be 6 and 8, can be 48 and 1, can be 12 and 4, so on and so forth. But when I say if this 48 number is converted into 2056 bits, can you find out A and B? In order to solve that factorization, your normal computer will take 4 quadrillion years to solve it, which is 1.5 times the life of the universe. Whereas your fastest supercomputer would take about 1.5 billion years. So we typically say what quantum has shown us that if you apply quantum computing and if you have less noisy data or let's say no noise and error in there, a quantum in synthetic case would be able to break it in few seconds or maybe in few hours. So security that we think is what you think of security today and in the future has a change that is coming in the next 2 to 3 years when quantum becomes much more pervasive in terms of what we're using. So summing it up before we get into the mathematics or the parts of quantum is there are two worlds, a physical world where we operate called the classical, a subatomic world where we say the quantum. Universe works in a dual way at a quantum level. It works as both wave and a particle. It cannot be either this or this. They occur both at some point. When your wave particles or wave functions collide, or when you measure somebody in a wave, it becomes a particle. And unless measured, a subatomic particle can actually exist in multiple states. And I don't want to go into multiple universes, but that is true. It may exist in whatever state it may be, unless you capture it and you try and measure it. And when you measure any particle, for example, which is essentially a wave, you would actually be given a classical measurement of 0 or 1. So your particle might be either 0, which may be a spin, it may be 1, which may be spin down or spin up. It may be the orientation of the particle in which you bring it, right? So that's the whisper at the power of computing. So taking off some myths, general anachronism, too arcane, too far off, it's for academicians and theorists. I don't think so, because there are companies now who are working actively on quantum. There are 8 startups in India. There are about 10,000 startups that have come up in the world. So it's a massive computing power change that has happened, a massive change in terms of how computation would change or how the fabric of computing would change. And the path to whatever you see as discovery in the future or the exploration requires a kind of hybrid computing between AI and between quantum that you do. So let's go to basic principles. One of it you already know. I told you that the light bulb can either be switched on or off in the classical world, which is called the bit, 0 or 1. In the qubit, you can actually lie somewhere in the middle as a superposition state where both 0 and 1 exist. So essentially speaking, if you've got one bit, you can either have it either 0 or 1. In the quantum world, you can have a combination of both 0 and 1. So it gives you a power of computation over there. So if you've got 2 bits, so if you've got 1 bit, you can only do 1 calculation. In quantum, you can do 2. If you've got 2 qubits or 2 qubits, you can do 4, which is 2 raised to power n. The computers that you are sitting on has got 32 bits or 64 bits, depending on what computer you use. If you've got 2 raised to power 64 powers of parallel computation, that is equivalent to the number of stars in Milky Way galaxy. So you already have the power within your hands to do a large amount of computation. The second facet, which is very, very interesting for quantum, is this facet called entanglement. Sometimes a pair of particles behaves as a complete unit. And what happens is, I've shown you 2 particles over here. I've shown you a blue particle which is spinning up and a red particle which is spinning down. So you can actually think of it like spin up and spin down like this. Now, the challenge is sometimes these particles get entangled and make one common system. So much so that, let's say I take the blue particle and I actually put it in my pocket without looking at it. I then allow my friend to take the red particle to the end of the universe. The moment I see this particle, which is blue, or I encode some data or I measure it, at that very instant, the particle which is red will eventually become the opposite sign or the same sign, depending on how they're entangled. What I'm talking to you is so counterintuitive that Einstein called it as a spooky principle of entanglement, which means that this entanglement belies the formulae for space, time, and also the kind of communication that we today are faced on, saying that light has, the speed of light is constant, it's the fastest in the universe. This entanglement happens to be without and belying that structure of space, space and time. And the idea behind entanglement is that I don't know one of the particles, what would they formulate? It's like throwing a coin. If you throw a coin, you would either get heads or tails. There's a probability of 50% of landing heads and tails. I've got another coin. I can still throw it up. I've still got the probability of 50% of landing that coin. But these coins, when they get entangled and they move away with large distances, when this coin shows head, I am sure that the other coin also shows tail or also shows head, as the case may be. So the idea is that the system becomes whole as a part. And how do we use it? It's very simple in security. If you're sending some keys over an internet and a hacker tries to hang on to that keys or spoof it, you immediately know that somebody had clicked it because of entanglement, because this key is now transferring as a part of an entangled pair. So you can catch that and you can change the encryption mechanism the way you see it. The third very counterintuitive case that you see is, if you roll a ball above a barrier, which is a heighted barrier, and you, depending on the amount of kinetic energy that this ball has, the ball would cross the barrier. If the ball does not have that kinetic energy, it won't. In quantum, even though the ball does not have that kind of energy, sometimes it may come on the other side of the barrier. In other words, if you look at it, the idea is that when you throw, and you've all played cricket in some format at some point in your life, when you throw a tennis ball at a glass window, 2 things are possible. Either the glass window breaks and the ball goes on the other side, or the ball just bounces back the glass window and the glass window stays there. You've never in your life encountered a phenomena where the ball goes on the other side of the window and the window doesn't break. This happens in quantum because particles are generally waves, and when these waves collide with a solid plane or a barrier, they have the probability of coming out on the other side as well. And this is a real experiment that I'm actually showcasing you over here. There is an electron that is actually bumped against a wall, a solid wall, and you would see a small fraction of that electron coming on the other side of the wall as well, with almost the same energy as it came. So I'll play it again. The electron bounces against the wall. A very light impression of an electron is coming on the other side of the wall as well. This is called quantum tunneling. It has many advantages. One of the facets of quantum tunneling is to help machine learning for optimization. But I think one of the other facets that I told you was, this is quantum tunneling that will be produced as a result when chip sizes are reduced to a very, very small point, because some of the electrons may cross across the barrier to the other side and may start producing errors. And that's why there's a demise of the transistor coming in. Now, there are different types of quantum computers. Some of them are called annealers. They're also called adiabatic. They can do some kinds of calculation. They really look at energy and Hamiltonians to solve a problem. Others are analog, some of them are universal computers, and we have not reached the universal quantum level, although there are different companies who are actually working in. This is how that looks like. This is an example that I'm giving you both from D-Wave, a quantum computing company, and IBM. Um, the important thing about these quantum computers is there's only a small chip which is placed right at the bottom. All of these copper wires are basically meant to give RF signals to this particular chip. And what they do is they actually keep this chip at a very, very cold condition, almost at the level of minus 273 degrees Celsius, which is colder than interstellar space. And the reason for that is at this particular level, we do not really have we do not have all the other effects of heat, etc., that is coming in. Another interesting thing is the fridge is the only thing which actually causes which is actually causes some kind of heat. So there's no residue that comes in. The superconducting processor that is there does not generate any kind of heat over there. The intuition for annealing is that everything in the and this particular quantum computer that I'm actually showcasing you from D-Wave is an annealer. From IBM that I'm showcasing you on the right is more generally a kind of superconducting qubit or superconducting transmon system, which is essentially working. Now, what's the principle of annealing? If you look at the intuition of annealing, everything in this particular universe has the ability for energy to go down, to stabilize. Energy always decreases as we as a human being. We always age because the entropy always starts increasing and the energy starts decreasing. Why can't we use this particular phenomena of physics and science to actually code some of our problems so that they optimize better? So the idea is very simple, even though this word is very difficult to understand. It's called Hamiltonian. What it really means is a function that if you put in your put in your physical system, it calculates the energy of the physical system. Something like saying that the apple on top of a table has got high potential energy than the apple at the bottom of the table, which is actually sitting on the ground. So we look at the Hamiltonian, we encode our problem in terms of the Hamiltonian on that particular system. And when the system drops down, because obviously physics allows us to drop down and decrease energy, we do find the real optimized solution for that particular problem. And that is something which has been our things as well. Now, what's the applications today? Hundreds and thousands, right? So solid state material analysis, molecular dynamics, chemistry computations, in optimization, radiotherapy, how do you place satellites, traffic flow controls, finance. There's also machine learning formulae, for example, finding Higgs boson, formulae for terrorist networks, so on and so forth. There are some practical things that have been put forward, and one of the first ones that I'm showcasing you is an activity from Volkswagen, which was done in the world, and this was using quantum computers to actually develop a good logistics route map so that there was a route optimization in terms of how taxis were driving. And this was using less energy and also less amount of data than an AI system would utilize. There's another company called Denso. They have used the quantum computation to actually give a 15% improvement as compared to their legacy systems for their automated guiding vehicle, which is again fantastic because you're actually utilizing some of these principles of quantum. There are some companies like Vuxi Next Code who are using who are actually using quantum to get genomics, about genomics data, and figuring out what's going on over there. And then there are certain other sources that I'm giving from IBM. There are quantum computing use cases in airlines. There's quantum computing use cases in financial markets. It's there in chemicals and petroleum. You can all read about it. There's also healthcare and life sciences in a big way that these sources really come in. Now, why do we get in? I don't know how many of you understand this, but I think if you are reading science and if you are doing computation and computing, you would have come across cases of vectorization, of course, but linear algebra. One of the first things that you have to understand for quantum is linear algebra and the vector spaces. And what we say is that the Hilbert space or the Hilbert vector space, which is the space for inner product join, is exponentially large. The reason why quantum can be used in quantum computing is because we've got enough space to play around, and so that which is not possible in the classical world. Why and how is it possible? It's because of this. Number one, your classical bits are represented by 0 and 1. The quantum bit is represented by this funny symbol called a dash and a greater than sign, and this is called the ket notation. This was, of course, given to us by Paul Dirac. if you combine two, you can actually get a bracket, and the other reverse part of it, or the counterpart of the vector space, is actually called the bra. So that's the complex conjugate of the ket. That's what it is. And how is it represented? You always represent 0 as 0 and 1 as 1. In the quantum notation, ket 0 is represented as 1, 0. So it's a vector, and it's a column vector which is represented, which has got, and think of it like saying that 1 is at the place where 0th element is of your array, and 0 is at the place where the first element is of the array. So if you're representing somebody as ket 0, you're obviously saying that it is 1, 0, represented as one column vector, whereas ket 1 is represented by 0, 1, which you're essentially saying that it is 1 at the place where 1 is notated. These two vectors are orthonormal. When they say orthonormal, they are orthogonally inclined, and they are normalized as well. So they actually appear at 90 degrees to each other. So if you actually take a kind of inner join of these, they will actually yield 0. But if they actually do inner join with themselves, they will yield 1, which says that they are orthogonal, they're orthonormal as well. Which simply says like this: if one bit has to be presented, you are actually giving two possible combinations. So if you go 2, it means 4, it gives you 3, which is 8, which is 2 raised to power n, which essentially is giving you the power of computation that you wanted. All of you know matrix multiplication, so I'm not getting it. A matrix is actually multiplied by this. It's multiplied because some components of this particular, the n vector or the n space of dimension is meeting the m space of dimension, and as a result of that, the resulting vector is this. So we don't want to go into review matrix multiplication, but I do want to review with you, if you want to go into mathematics, is a tensor product. Most of these vectors in quantum computing are shown as tensor product of vectors and not normal joins. And when you say a tensor product, it's very, very simple. If 3 and 4 and 5 or 6 are tensor product, it's represented by this symbol called cross and a circle over here. It means that this particular vector is multiplied by each one of them. So 5 and 6 vector is multiplied by 3, and 5 and 6 is multiplied by 4, which increases the space to about, from 2 by 2 or 2 by 1, it increases to 4 by 1. And if you then do a tensor of 1 by 2, you can actually get an 8 value space over here. So if you have 3 vectors in quantum space doing a tensor product, you're essentially getting 2 raised to power 3 combinations, which is essentially 8. And that's what we talked about, the whisper of the power of computing, or what quantum does. And when you want to represent multiple qubits, which you're representing as 0 and 1, it's very, very simple. If I'm actually doing a tensor product between qubits 0, ket 0 and ket 1, ket 0, as I told you, is represented by 1, 0. Ket 1 is represented by 0, 1, as you saw earlier. You just want to do a tensor between the two. So this 0, 1 actually gets tensored and get multiplied by both 1 and 0. So you essentially get a number which is 0, 1, 0, 0. Your two qubits, when they tensor together, have actually now become 4, which is again the power that you're essentially giving in. Now, obviously, when you have to move a vector, when you have to transform a vector, you have to look at matrices. Matrix is one of the best examples to transform it. And that formulates the quantum gates. You know classical gates, you know NOT gates, you know AND gates, you know NAND gates. For building a quantum computer, you obviously know quantum gates. And these quantum gates are defined by these matrices. So for example, if I want to flip a qubit, if I want to flip a ket 0 to ket 1, I would actually just apply a quantum gate, which is called the quantum NOT gate or the X gate. And if I multiply it with my vector, it'll change the sign. It'll flip the sign. I can also flip it on a Z angle. I can have it in superposition like a Hadamard, which is things that you would learn. I can even do some other brilliant operations on a circuit so that I can formulate them in terms of quantum gates. These gates are actually implemented inside the quantum computer. So for us, if I have to do a calculation, I would go over the cloud, I would go into the quantum computer, and I would run my calculation by applying these circuits and these gates over there so that I can get the result which I actually wanted. So since you are joining in from an IIT BSc course, one of the things that is done over there is obviously AI. AI has become pretty normal. A large part of the people today consider AI as the second fiddle because everybody wants to talk about AI. This is something which we are saying that the machine learning now is also turning itself into quantum machine learning. And There are 4 spaces in which we work, which you see the figure on the left-hand side. You see one of the principles is CC, which says classical data applied on a classical system or a computer. Quantum data applied on a classical computer. Classical data applied on a quantum computer and quantum data applied on a quantum computer. What we are interested in largely is classical data applied on quantum computer. And how do you apply it? You simply apply it in the normal mechanism that you do your machine learning. What have you done up till now in machine learning, or your teachers would have told you? Take data, train the data using a model. The model has a function which has got data, but also a parameter called theta, which is trainable. Once you get the answer from that model, there's a cost computation value. The cost computation goes through a gradient descent, which you try and maneuver theta so that the model becomes better. All I'm saying is that data, cost computation, and gradient descent remains the same. But the model now becomes a model which needs to be applied on a quantum computer. So that becomes a quantum machine learning model. How do you want to do that? We actually say that this is called quantum modeling. Anything coming from the left-hand side, this figure is called psi or ket psi. This really represents the wave function or a qubit that you're getting in. It goes through a particular gate mechanism. You measure it, and then you apply all the other things. You will also see somewhere in the literature people talking about this as variational models or parameterized quantum models. They're also called as ansatz. But how do you look at it? First things first is, I've got data in classical format. How do I encode this data? And I want to encode it in form of quantum computing. So let's say, for example, my classical data consists of a vector of 2 elements, which are x1 and x2. And I want to encode this into my quantum computer or quantum gates. Best way is, or one of the easiest way was basis encoding, which says we take 2 qubits and we make sure, because this says x1 and x2, x1 1 becomes 0 1 and x2 becomes 1 0. So I'm just encoding my qubits to that value. Rest of the other things I can keep it 0. There's another mechanism where we can actually encode the amplitude. So I rotate these qubits in a format that the amplitude of the vector or whatever I get in classical data remains the same. And the part that I like the best is called angle encoding. So let's say you have a vector x1 which has got values like 0.8, 0.1, 0.1 or whatever, and you've got 4 qubits representing it. Each qubit is rotated at an angle using a gate to represent this particular system. Now, when I say rotate the qubit, we are actually saying that in a kind of Q sphere, you're rotating the qubit to that particular angle, and you're actually transforming or embedding that space over there. There's, of course, other things like higher order encoding data. Now, the other process is, once you have encoded data, you want to apply the model. And this is a generalized model. You rotate those qubits again, you apply some entanglement into that system, and that's where the product really comes out over there. And then you do measurements and you repeat this, right? So you repeat the even parity, you repeat the odd parity, so on and so forth. You've made the model, you want to do a cost computation, and you want to apply a gradient descent on top of it. One of the other ways of applying gradient descent in quantum is to take a qubit, take the parameterized system that is there, and add a value of S. So you move up a domain, or you move up a certain level and you move down a certain level to actually get a kind of gradient over there. And that becomes a gradient descent. So what I'm essentially trying to do, some of you may not understand this at this time, but if you're doing AI, you would understand the basic premise that all that we are trying to do is that the field that is gaining prominence today is quantum machine learning, which really means is that your data, which comes on a classical world, now has the ability to be applied on a quantum computer to get some value out of it, or to get some more value out of it, which classical AI could not do. What are we doing? We are actually doing a process of drug discovery, and we're actually applying exactly the same circuits, which are called quantum hybrid GAN generators, in terms of what we can see whether small molecules get generated. And this is just a circuit diagram for the same. For people who actually are interested, they can actually reach out to me and we can work out in terms of what we're doing. The advantage of India and where you're sitting, the potential is about $310 billion, where we are looking at cumulative value to be added to Indian economy by 2030. This is a NASSCOM report. And we are also looking at opportunities from agriculture, from financial services, from healthcare and life sciences, from telecom and broadcasting, and you call it. Almost every field where you are today applying AI would shift in a way where you're essentially looking at quantum computing in terms of changing the way that we look at you, right? So the only thing needed, and I wanted to end this with a slide because it's already 45 past 5. My only suggestion to you would be, if you need to get into this particular world of quantum computing, it's wonderful, number one. Number two, it's growing in its importance today. It's also looking at young engineers on how they can produce it. So make sure that your linear algebra is well defined, your vector spaces are clear, you've got some concepts of quantum physics, even though not, you know classical logic gates, you know some programming languages like Python or C Sharp, so that you can get into this world. And you know basics of machine learning and AI. In fact, basics in terms of whether you've implemented some data on machine learning and AI. If you've got this, you can enter this non-trivial world. And this non-trivial world is just glaring at its face at this time for us, in terms of what it can do and what it can. So, for example, climate changes, nitrogen fixation, finding out satellite placements in terms of what we do for our telemetries and so on and so forth. Huge advantage. So I'll end my talk over here and look forward to your questions. But quantum computing is here to stay. It's changing that fabric. And my session today is only to let you know that there is a field open out for each one of you to get into it. Thank you.
Thank you so much, sir. That was a really insightful session. We already have a few questions in the chat box, so I'll start with the first one. Someone asks, isn't AlphaFold open sourcing the protein structure?
They are, and that someone is very right. I think AlphaFold has done it on AI, but I think we still have a lot of problems in terms of finding out the right molecule against the right virus. What AlphaFold has done is they have actually done, and they've done really well. And in order to commend them, they've actually used AI to make sure how proteins really get folded in terms of some space. I think the challenge is much more bigger now. The challenge is that when you're talking about drug design is really like a lock and key mechanism. So basically, the virus is the lock, and you have to fit in your key into the virus, and you have to figure out that particular molecule that fits into a key. Now, some of these molecules are available, but most of these molecules may need to have been generated. And for that, we are saying that the space becomes much more broader, and that's why quantum would help us over there. And that's the whole idea.
Another question is, how do you calculate life of the universe?
How do you calculate? I think so that's a good question. The life of the universe is really calculated in terms of some what do you call, in terms of some probabilities. Nobody knows what's the life of the universe at this point. What we do say is that within the frame of mind and within whatever we have seen as redshift and red bubble shift, whatever we're seeing, right? The Hubble shift that we've seen, possibly sometimes it could be 25 quadrillion or 40 quadrillion years. But that's a very vague terminology. There's no, there's of course a lot of scientists and astrophysics who are actually working onto it. But the idea behind saying that over 40 quadrillion years was really saying that it's absolutely uncrackable if you use your classical computers to break an RSA algorithm. That was the whole idea behind it.
So another question is, what is RF signal?
So it's a radio frequency signal. I think what happens is that at that particular level, we don't want to trouble the atoms and the superconducting liquid too much. And we also want to make sure that we do some kind of an impact onto it, because computers, what you do, you have to give electrical signals to make sure that your gates move up and down, your voltages change. Over here, these are RF signals which are actually sent in. These are microwaves which are actually sent in to change that material so very slightly that they help you in that computation.
Could AI with quantum computing be able to create a black hole by trying to calculate Graham's number?
Yeah, I have no clue whether that would. I think there's been a lot of talks about quantum and all of these things creating a kind of black hole into the system, but I don't think that is possible. I don't even think we've got the wherewithal and also the kind of processing power at this time to do that. Graham's number, yes, it's not been sorted out at this point in time. There's also certain Riemann's hypothesis which has not been solved, but I don't think we'll be able to create a black hole based on that.
So from optimization point of view, how loss function is calculated? Is Hamiltonian used here?
Yeah, so from an optimization point of view, Hamiltonians are the loss function is not calculated. The Hamiltonians are moved. So, for example, before you apply annealing, you actually start off with the current Hamiltonian, and the objective Hamiltonian is kept smaller. Once this system evolves, and when it decreases the energy, the Hamiltonians shift position. So the one that you coded up earlier actually drops down and this one goes up. So it's basically saying that my problem optimization came up and this was the solution because I wanted to find the global minimum. The idea of annealing, and that's why it's very restrictive in terms of optimization, is I want to find the global minimum for the answer that I'm actually getting across. And I am not really looking at loss functions. Loss is when you're essentially trying to do optimization using neural networks and some others, where you have an error which comes in, and that error needs to be corrected in some format to be given back to the ecosystem. So,
So there's a question asking how will it impact agriculture? And another question of the same sort is it related to gaming?
is it related to, sorry, gaming?
Gaming, yeah.
No, I don't think it's related to gaming, but I think it's related to, in agriculture, there are huge things, right? So for example, nitrogen fixation is a huge challenge. And quantum will actually help us solve nitrogen fixation in a big way in terms of what more varieties of plants and what we are looking at can actually look at more nitrogen in terms of fixating, right? So we already know that from an agricultural point of view, the kind of soil that we have today is quite parched, and there's a lot of work that is being done to make sure that that soil is not that hungry anymore. There's got a rich life and ecosystem. One of the things that plants do is essentially fixate nitrogen. They capture nitrogen, and that is what the nutrients are from the soil. So we are losing out. Can this be a mechanism to do that? Second, carbon sequestering. How can you do carbon sequestering using different techniques, right? Third is weather and climate pattern change. You've all seen it. You're all part of it. You've all grown looking at it, saying what was the weather 10 years back has completely shifted in today's world. It's just a very, very rapid change in terms of how weather patterns really come out. Can we look at some of those, right, in terms of very, very hard problems and put them to quantum?
So another question is, when do you think this will be at someone's desk?
No, I don't think it'll be a desk. It'll always be a combination of classical and quantum. I may be wrong. There are certain companies that have actually made 2-qubit quantum computers available at room temperature. But I think one of the biggest change and thing that we do is, in order to make these computations less noisy, we have to bring down the temperature to a very, very significantly low level, microkelvins and millikelvins. And at that level, we cannot really do it at room temperature and cannot bring machines at room temperature at the moment. So my suggestion, my ideology would be that quantum will always augment classical computing, will always augment the need for data that you want to put on quantum computers, but they would be quantum computers that are available to you over the cloud, and you will utilize them for certain functions, etc. They won't come to your houses.
Any book suggestions or resources we could refer to develop domain knowledge?
Oh, there's enough. I think there's quantum computing for computer scientists. There's quantum information systems. You can even go on YouTube and just do a search on quantum computing, and you've got hundreds and thousands of tutorials on which quantum computing really does. So there's no dearth of information. There's enough in the world at the moment.
How can data science be useful in the field of quantum computing?
It's already being used, right? So your data science is basically the initial part that you do before you get into a quantum machine learning, and also on the other side as well. So for example, you can have a classical data, you can curate it using data science and put it into a quantum machine, and that is called a quantum machine learning facet. You can also do reverse. You can have quantum data created by quantum computer and put it to classical machines to understand what's the analytics. Or you can do both of them. You can have a quantum data and a quantum computer to measure it. So it works both ways. There is data science everywhere.
What are the companies or startups in India which work in this field? What are the contributions of Tech Mahindra till date? If possible, could you give us some examples?
Yeah, so I think there are a lot of companies. I think some of the prominent ones that I can name you is Qnu Labs. There's a company which is actually making quantum security based hardware. He's a good friend. There is a lot of work being done in CDAC as institutions, and in your IIT Madras. I have a very good friend, Dr. Anil Prabhakar, who's actually looking at quantum computing and making quantum computing quite viable for the industry. There's obviously work being done in ICER. In startup world, there are some startups in Pune which are working. How do you do optimization, for energy charging and so on and so forth. So there are a lot of them. Tech Mahindra's contribution is that as a services-oriented company, what I run is an R&D division and a research lab. The idea behind us is how can we take quantum computing to some of our customers. So what we are looking at is 3 branches in which we are taking. One is telecom, one is healthcare, and one is, of course, financial services. And we were some of the first to actually have done a quantum computation use case, a quantum communication use case way back in 2018, when the field was not even known that much. So we got into it quite early. And now we are essentially looking at quantum machine learning to solve a lot of challenges for us.
Sir, how long will it take for the quantum computer to take over the classical computers?
It won't take over. That's what I answered last time. There's another question. It won't take over. They'll work in tandem.
Okay. What could be the relation between quantum computer and nuclear energy?
But it's quite connected, right? So at the end of the day, these are all fundamental particles that you're working on, right? So I don't know whether you know or not, but there are 16 fundamental particles of nature that we call it. 12 of them are something which are called fermions, which are basically called matter particles. And about 4 of them are called bosons, of course, named after Satyendranath Bose, our physicist. And these bosons are basically ones that carry force. If you talk about nuclear energy, there are 2 types of interactions that happen: the strong nuclear force and the weak nuclear force interactions. They carry a transfer between these bosons and fermions. And when we talk about quantum, we essentially say that it's a discrete packet of energy that is actually at a subatomic level. So there's a direct apple to apple match between quantum and nuclear energy. Even though both of them cannot be combined together, there is some work that is happening, which is basically saying, look, can we apply quantum computing to understanding and analytics of nuclear energy? But that's about what I know at this point in time.
Can quantum computing be the key to teleportation?
You never know. But teleportation is actually an algorithm in quantum computing. And teleportation really means how can you transfer, in terms of how can you transfer some information available at qubit at one point to a qubit at the other end without losing the amount of data. But I think teleportation like Star Trek, I am not so sure. That may not happen.
So someone has asked, can we do time travel?
So there are lots of theories and a lot of theorists who've actually written about time travel. I don't think quantum, of course, the essence is quantum, but there's no connection to quantum computing.
Are there roles available at Tech Mahindra in the quantum ML field? If yes, then what's the expectation in the first 3 months as someone who will be new and will have a learning curve for move into quantum?
There are some roles available now in TechM for the quantum ML field. I think the expectation is that you should at least have basics of or prerequisites of what I talked about, right? So at least you should know logic gates, you should essentially know physics, a little bit of physics, you should at least know linear algebra. And that's very important for engineers and even people in BSc degree. Should know what is linear algebra, should know what is vector spaces. But I think we don't expect people to know almost everything when they come down to an organization. We can, of course, train them as they go.
How can we use quantum computing to control the climate changes happening today?
I already answered this.
Okay. As you told, RSA can't be cracked using classical computing. What will be the impact of quantum computing on security as it becomes normalized?
So as it becomes normal, so there is already impact being having. There are already quantum standards being built up. What we say is that anything which is which includes mathematics in terms of formulating a kind of encryption technique can be broken down by quantum. Has not been broken down as yet, but would be broken down in the future. So there are post-quantum cryptographic techniques that have come up. There are quantum safe protocols that needs to be applied. So that work has already started.
Can quantum computers also decode SHA-256 like hash codes?
Haven't been found as yet. They can be.
NVIDIA just claimed that they can simulate a 40 qubit
NVIDIA.
system.
Yeah, I can read the NVIDIA's claim that they simulate a 40 qubit system using their works. Yes. So there is another branch which is called quantum inspired, which you say quantum simulation, which is correct, and NVIDIA just did that. So there are two ways in which you look at it. One is actually application of quantum computation on quantum computers, but also then there is simulation, which you can do on a classical computer, but that is not very, that is basically at this stage, which is at this particular level, because we have not got error-free quantum computers at this point in time. But once the error-free quantum computers do come in, which could be another 5, 7, 8 years or whatever, then we see it as then we see it as these quantum simulations not happening, right? So that's the yeah. So quantum computers can be disastrous like nuclear science done by nuclear. Any technology is as good and as bad to what you use. So I think yes, they can be, and yes, they can't be as well. So yeah, very interesting question. I quantum computers analogous at this stage or analog as this stage or digital? Yeah, so very interesting question. So they are somewhere in the middle, I would say. They are part of the computers. Analog quantum computers are called analog. There are also adiabatic computers. But what we are essentially trying, or what companies are trying to do, is to create a kind of digital system. Right? Computations may become analog in the middle.
Okay, so I think I think also there were some questions asking if there was any way possible we could acquire a PDF of the presentation you gave today, and also people were asking if if at all we needed some more guidance from you, how could we contact you?
Yeah, you can just search my name on LinkedIn. It's Nikhil Malhotra. I forgot the ID that I was using, but I think you would be able to find me. Just give me a second. I think it's Nick Malhotra 2000. I'm not sure, but I can just give you my ID. Something like this. I'm not very sure, but you can search me on the LinkedIn as well. Yeah,
So I guess there's
my-
like one last question.
yeah.
Any prerequisites of getting into computers, into quantum
Quantum computing.
computers?
I've
This
already
field
told this,
seems
right?
to.
You already seen.
Yeah, yeah.
I can share a PDF for this one for all of you. You can actually have a look at it. That should not be a problem.
Okay. Okay, sir. I think that's all for today's questions. Thank you so much, sir, for sharing with us your very, very precious time and answering all our questions so patiently. This was a very insightful session indeed. Sir, any words of wisdom you would like to share before we conclude today's meet?
No, it's been wonderful, and I think a lot of people stayed behind. I know the field is quite non-trivial, but I think the field's right there. So if you want to get into it, today is the time, and that's the time that you can get in, right? So, yeah. Perfect. Thank you,
Thank you
Bharvi.
so much, sir.
Thank you,
Thank
Bharvi.
you.
Take care. Take care. Bye. Bye, guys.
Bye.
Take care.